Welcome students, you are welcome to fifth part of chapter 1 in unit 3 higher order linear differential equations. In the fourth part of chapter 1 we have learnt about to find solutions of homogeneous linear differential equations of order n with constant coefficients for second case, that is when all the roots of auxiliary equation are real but some are repeating. To continue with the same chapter, we move on to find solutions of homogeneous linear differential equations of order n with constant coefficients for third case, that is when the auxiliary equation has imaginary roots. To solve a homogeneous linear differential equations of order n with constant coefficients, one first solves the auxiliary equation to determine roots. Based on the nature of roots, we can find general solution for f of dy is equals to 0. Here, f of dy is equals to 0 is the symbolic form of homogeneous linear differential equations of order n with constant coefficients. Now, let's see case 3, which arises while solving the auxiliary equation. In case 3, if the constant coefficients in equation f of dy is equals to 0 are real, then any imaginary roots exist for auxiliary equation. It must occur in conjugate pairs. Thus, if alpha plus I beta is one root, then alpha minus I beta must be another root. So, if alpha plus or minus I beta are two imaginary roots of an auxiliary equation and the remaining n minus 2 roots of auxiliary equation are real and distinct, then the general solution is y is equals to e power alpha x of c1 times cos beta x plus c2 times sin beta x plus c3 times e power m3x plus so on plus cn times e power mn x. Now, if alpha plus I beta and alpha minus I beta each occurs twice as a root, then the general solution is y is equals to e power alpha x of cos beta x of c1 plus c2 times x plus sin beta x of c3 plus c4 times x plus c5 times e power m5 x plus so on plus cn times e power mn x. Now let's see some example problems for case 3. First example, solve d square y by dx square plus 4 times y is equals to 0. Now find the general solution of the given differential equation in example 1. To do this, first write the given differential equation. Next write the symbolic form of the given differential equation, which is d square plus 4 of y is equals to 0. Therefore, we get f of d is equals to d square plus 4. Now, in f of d, replace d with m. We get the auxiliary equation like this. F of m is equals to m squared plus 4 is equals to 0. Now find the roots for the auxiliary equation. F of m is equals to 0. Now we have f of m is equals to m squared plus 4 is equals to 0. Now in this equation, 4 is replaced with minus 2i whole square. So we have m square minus 2i whole square is equals to 0. Now m square minus 2i whole square is equals to 0 can be written as m plus 2i into m minus 2i is equals to 0. Since we have m square minus 2i whole square is equals to m plus 2i into m minus 2i. Thus we have m plus 2i into m minus 2i is equals to 0. Now from this equation we have m plus 2i is equals to 0 and m minus 2i is equals to 0. Now from these two equations we have m is equals to minus 2i and m is equals to plus 2i. Therefore, m is equals to 0 plus or minus 2i are the roots for the auxiliary equation, which are imaginary roots. Now using these roots, we write the general solution for the given differential equation like this. Y is equals to e power 0x of c1 times cos 2x plus c2 times sin 2x. Here e power 0x value is 1. So we have y is equals to c1 times cos 2x plus c2 times sin 2x, which is the general solution of the given differential equation. Let's see one more example for case 3. Second example, solve dy by dx minus y whole square into d square y by dx square plus y whole square is equals to 0. Now find the general solution of the given differential equation in example 2. To To do this, first write the given differential equation. Next, write the symbolic form of the given differential equation, which is d minus 1 whole square into d square plus 1 whole square of y is equals to 0. Therefore, we get f of d is equals to d minus 1 whole square into d square plus 1 whole square. Here in f of d, replace d with the m. We get the auxiliary equation like this. F of m is equals to m minus 1 whole square into m square plus 1 whole square is equals to 0. Now find the roots for the auxiliary equation f of m is equals to 0. Now we have f of m is equals to m minus 1 whole square into m square plus 1 whole square is equals to 0. From this equation we have m minus 1 whole square is equals to 0 and m square plus 1 whole square is equals to 0. Here m minus 1 whole square is equals to 0 can be written as m minus 1 is equals to 0. Again m minus 1 is equals to 0. Here, m square plus 1 whole square is equals to 0 can be written as m square minus I square whole square is equals to 0. Since 1 is replaced with minus I square in the equation. So we have m square minus I square whole square is equals to 0. Here, m minus 1 is equals to 0 gives m is equals to 1. Again, m minus 1 is equals to 0 gives m is equals to 1. Now, m square minus I square whole square is equals to 0 can be written as m plus I into m minus I whole square is equals to 0. Since we have m square minus I square is equals to m plus I into m minus I. So we have the equation m plus I into m minus I whole square is equals to 0. We have m plus I into m minus I whole square is equals to 0. So we get m plus I whole square is equals to 0 and m minus I whole square is equals to 0. From these two equations, we have m plus I is equals to 0. Again, m plus I is equals to 0 and m minus I is equals to 0. Again, m minus I is equals to 0. From these four equations, we have m is equals to minus I, m is equals to minus I and m is equals to I. Again, m is equals to I. Previously, we have m is equals to 1 for 2 times. Finally, therefore, m is equals to 1, again 1, and 0 plus or minus 1i, again 0 plus or minus 1i are the roots of the auxiliary equation, which are real and imaginary. And these roots are repeated roots. Using these roots, we write general solution of the given differential equation. Here, the root 1 is repeated for 2 times. So, the independent solution will be like this. C1 plus C2 times x of e power x. Here, the conjugate pair 0 plus or minus 1i is repeated for 2 times. So, the independent solution will be like this. E power 0x of C3 plus C4 times x of cos 1 into x plus C5 plus C6 times x of sin 1 into x. Using these two independent solutions, we have the general solution like this. Y is equals to C1 plus C2 times x of e power x plus e power 0x of C3 plus C4 times x of cos 1 into x plus C5 plus C6 times x of sin 1 into x. Here, e power 0x value is 1. Thus, we have y is equals to C1 plus C2 times x of e power x plus C3 plus C4 times x of cos x plus C5 plus C6 times x of sin x is the general solution of the given differential equation. Now some practice problems are given related to case 3, that is when the auxiliary equation has imaginary roots, to learners for practice. So learners try to solve these practice problems. In the next video, let's see the preliminaries of chapter 2, that is solutions of non-homogeneous linear differential equations of order n with constant coefficients. Let's see what we have learnt so far. We learned to find the solutions of homogeneous linear differential equations of order n with the constant coefficients in different cases that arises while solving for the roots of the auxiliary equation. That is, first case when all the roots of auxiliary equation are real and distinct. Second case, all the roots of auxiliary equation are real, but some are repeating. Last case, the auxiliary equation has imaginary roots. We will meet in the next video lecture, students. Thank you.